Acids and bases are chemicals that aren't only found in a science lab. There are many different acids and bases that we can find in our household products. This lesson is on acids and bases. So, acids, bases, and neutral solutions have properties that are used to classify them. Acids are able to conduct an electric current because they're an electrolyte. They have a pH of 6 or less. They're corrosive. They react with metals and they taste sour. Now, we should never taste acids that are in a lab, a chemistry lab, but things like lemon juice or vinegar are examples. Bases conduct currents as well. They're corrosive. They have a pH of 8 or more. They feel slippery and they taste bitter. And again, there are certain bases that we should never taste, but then there's other ones like a mixture of baking soda and water that you would notice has a very bitter taste. Neutrals have a pH of 7, and they can be electrolytic or not, depending on what makes up their solution. We have 4 types of solutions: neutral molecular solutions, which are composed of nonmetals only. These have no effect on litmus paper. Neutral ionic solutions, which are solutions composed of ionic compounds of metals and nonmetals together, and they again have no effect on litmus paper. Now, neutral ionic solutions would be able to conduct electricity, but neutral moleculars won't. Acidic solutions are compounds that produce hydrogen ions, and it will turn litmus paper red. Where basic solutions are have compounds that produce hydroxide or OH negative ions, and these turn litmus paper blue. So blue for a base. So when sulfur and nitrous oxides get into the air, water molecules can form on them, and it can cause acid deposition. Now, there are 2 types of deposition. We can have wet acid deposition, which is when emissions that contact precipitation and fall to the ground as rain and snow. We can also have dry acid deposition, which is when gases and particles are absorbed by the earth or deposited on any surface. And in Alberta, most of the deposition of emissions is in the form of dry deposition. So when we look at these images, we can see that sulfur dioxide and nitrogen oxides are released in the combustion of different fossil fuels. And when they combine with water in the atmosphere, they can form nitric acid and sulfuric acid, and then will fall to the ground as acidic precipitation. Now, they can leach chemicals from the soil and change the pH of water bodies, which affects the plants and animals that live in there and can cause direct damage to vegetation. When we look at hydrogen ion concentrations that can tell us about pH made at field laboratories, we can see that in the Northeast United States and then also in Eastern Canada, we typically have a much more acidic soil and water than we do in Western North America. And this is partly because the soil in Western North America contains a little bit more limestone, which acts as a buffer, as well as most industry, when it comes to refining metals and ores, happens in the Northeast United States and Eastern Canada. And these are the industries that can produce a lot of sulfur and nitrogen oxides. So when we look at our acids, they can be classified by the properties or by their chemical composition. So acids are molecular compounds, but they behave like ionic compounds when dissolved in water, so they form an electrolytic solution. The water molecules are able to break apart the bonds in the acids, and charges can now move in a direction. So now they're able to conduct electricity. So there's a force that pulls oppositely charged objects toward each other, and this is electrostatic attraction. So positive charges are attracted to negative charges. Water pulls those positive ions towards the oxygen end of the molecule, and hydrogen pulls the negative charges towards the positive end of the molecule. And then dissociation occurs when those 2 ions separate into different charges. And then once dissociation occurs, we now have an electrolytic solution. So, Savante Arrhenius formulated a theory in 1887 that all acids have hydrogen ions and bases have hydroxide ions. Now, there's a few problems with this theory. Not all acids and bases have a hydrogen or hydroxide ion. Hydrogen ions cannot exist in water because it's so positively charged. It actually will form H3O, which is a hydronium ion. So the hydrogen will join with a water particle. And then that hydronium ion is going to be responsible for the acidic properties. So if we looked at this little diagram here, we won't actually have a hydrogen ion free floating in that water. It will have joined onto a water molecule and form H3O in water. So when we're looking at the Bronsted-Lowry acid-base reaction, this describes the reaction of the action of the acids and the bases during a chemical reaction. So there's going to be roles in the reaction. Are we a proton donor or are we a proton acceptor? So the proton donor is going to be the acid donating a hydrogen ion, and the base in a reaction is going to accept that hydrogen ion. So the products that formed are going to be the conjugate acid. So that's formed when the base accepts the hydroxide ion. And our conjugate base is going to be formed when the acid accepts the hydrogen ion. So when we're writing these reactions, the loss of a hydrogen ion by an acid, creates a conjugate base. So then we're going to recognize this in the formula because there's no hydrogen ion in the formula anymore. Now the gain of a hydrogen ion by the base is going to be now known as a conjugate acid. We're going to recognize this because there's been the addition of a hydrogen ion. And there's a page in your data booklet on page 12 to identify which is going to be the acid and then its conjugate bases. So we're going to follow these steps in a Bronsted-Lowry reaction to write our acid-base reaction. We're going to find the two solutions that are reacting and identify the acid and the base. The stronger acid is going to be higher on the table. So if both are listed on our acid table, we're going to choose the one that's higher up and label it as the acid. The other solution is going to be our base, or it could be a weak acid, but we're going to identify it as our base. Now we're going to write the reactants side of the equation. We're going to find the conjugate form of the acid and the base, and we're going to write them on the products side of the equation. So for an example, if we have an acid, it's going to be acetic acid, CH3, CO2H, and then its conjugate base is going to be CH3, CO2 negative, or ammonium, NH3, to the ammonia amide ion of NH2 negative. So the hydroxide ion is going to pick up a hydrogen ion by attaching it to one of the lone pairs of oxygen. Ammonia picks up a hydrogen ion by attaching it to the lone pair of the nitrogen, and water can pick up a hydrogen ion by attaching it to one of the lone pairs on the oxygen. So for an example, write the formula for the conjugate acid of fluoride ion, hydrogen sulfide, chromium oxide, and ammonia. So in each case, the formula for the conjugate acid is derived by adding one hydrogen ion. So we're going to have HF, NH4 positive, H2SO4, and HCrO4 negative. So the hydrogen has added one positive charge to those compounds, as well as we can see the hydrogen in the examples. Now to identify conjugate bases. So write the formula for the conjugate base of the following acids. So to have a conjugate base, we're going to remove a hydrogen ion from the following acids. So instead of HClO3, we're going to have ClO3. Instead of H2SO3, we're just going to have HSO3. Instead of H2O, simply OH negative. And instead of HCO3 negative, we're going to have CO3 negative. So again, the Bronsted-Lowry theory of reactions is our acid is going to be a proton donor and our base is going to be a proton acceptor. The conjugate acid is formed once that compound, the hydrogen, has joined the base, and our conjugate base is formed once the acid has lost its hydrogen ion. Now, we used lasers to capture images of the motion in chemical reactions, and it helps confirm our Bronsted-Lowry theory of acids and bases. And this will help predict the outcomes of acid-base reactions. Now, continuing on with the issue of acid deposition, emissions that are from human sources are known as anthropogenic, and this is typically from the combustion of energy sources, so biomass fuels as well as hydrocarbon fuels. Now, these emissions combine with water to form acid rain or acidic precipitation if it falls as snow or sleet or hail. Now, that rain is acidic due to natural and human sources, and the degree of acidity can be measured using pH. So the lower the pH, the more acidic the rain. pH is measuring the amount of the hydronium or H3O positive ions in a solution. And the number of hydronium ions influences the reactivity and the amount of base needed to neutralize or to react that acid. The pH scale was developed in 1909 by Sorensen, and it was designed to measure dilute acids, and every step on the pH scale is 10 times different. So our pH scale measures from 1 to 14, 1 to 6, numbers 1 to 6 are acidic, number 7 is neutral, and 8 to 14 are base. And if you go from 6 to 5, you now have something that's 10 times more acidic. So here's an image of the pH scale where we can see that gastric juice and lemons are very acidic, where Tums and soapy solutions or milk and magnesia are very basic. So pH stands for the power of hydrogen, and it corresponds to the hydronium ion concentration in moles per liter. Now, here are the conversion equations for hydronium ions to pH, and they're going to be in your data booklet. So we can convert from pH to moles per liter and then back again. So if there's a pH of 5, then our hydronium ion concentration is 10 to the power of negative 5. And if our hydroxide, and then to calculate our hydroxide ion concentration, that would give us 0.0001. We can convert between these two. So again, these formulas are in your data booklet. So if you're given pH and you go 10 to the negative pH, you're given your hydroxide ion concentration. And if you're given the hydroxide ion concentration and you want to find pH, you take negative log, and then you put in your hydronium ion concentration to get the pH. So what is the concentration of a hydrogen ions for an acid with a pH of 4.56? So we must take an inverse log. So this is probably going to be a button on your calculator that says negative log. It might be a second function button, so check out that. Then you're going to type in your calculator 10 to the power of negative 4.56, and we get 0.0000275542, or 2.8 times 10 to the power of negative 5 moles per liter. So we have everything correct in our significant digits. So you have either a 10 times button on your calculator, or in some of the TI-83s, you have that little up caret button, which looks like the little hat to get that exponent. So, and we really need to make sure that we put in the negative sign before we do the 4.56 to get the hydronium ion concentration. So we can also calculate the pH of a solution where we're given the hydronium ion concentration. So we can easily do this if we have a 1 followed by zeros, because we have to do times 10 to the negative 3. Because of negative log, the answer would be 3. But pH is not written to reflect the number of significant figures in the concentration. So our pH value should also reflect 3 significant figures. So in pH and pOH, the only place where significant figures are contained is in the decimal portion. So the correct answer to the above problem would be 3.000, because we need to have 3 significant digits past the decimal place. So if we have our hydronium ion concentration at 0.00100, we need 3 significant digits, and those would be our decimal places. But these ones are very easy to calculate. Again, if we are given our hydronium ion concentration, we take our equation, pH equals negative log hydronium ion concentration. So this is negative log 1.89 times 10 to the negative 4, close bracket, and we get a pH of 3.723, because again, 3 significant digits in pH are only behind the decimal place. This is then going to be an acidic solution because the pH is less than 7. So to convert pH to hydronium ion concentration, again, we're going to take 10 to the power of negative 7, 10 to the power of negative 11, 10 to the power of negative 2, 10 to the power of negative 4, and 10 to the power of negative 14. Now, sometimes we'll have pHs with decimals, so these will have a little bit of a varied answer. So to calculate our hydronium ion concentration, so pH of hydronium ion concentration of 10 to the negative 3 will give us a pH of 3. A hydronium ion concentration of 10 to the negative 5 would give us a pH of 5. 10 to the negative 7, a pH of 7, and 10 to the negative 10 would be a pH of 10. So you can see the pattern there between the exponent and the pH. So indicators such as litmus paper are used to indicate the rough pH of a substance. Now, First Nations used to use natural acids to adjust the color of the dyes they made from leaves, berries, and bark. So this would be an indicator that could that changed color. So common indicators are shown on table 12 of your data booklet, and these are chemical indicators, and they're used to measure the pH of a substance. So sometimes you'll be given a series of what has happened when a solution has been added to 3 different indicators, and then by looking at the range of pHs and their color changes, you'll be able to identify a range of pH of that solution. So if we see here, methyl orange goes from red to yellow between a pH of 3.2 and 4.4. And then bromesquirrel green goes from yellow to blue between a pH of 3.8 and 5.4. And we put an acidic solution into both methyl orange and bromesquirrel green, and it stayed yellow. We would assume that that pH was between 3.8 and 4.4. So when we're given the information, we can use that chart to determine a rough pH of those solutions. So if we put phenolphthalein in a solution with a pH of 12.7, if I go back, phenolphthalein goes from colorless to pink once that solution has gone up to a pH of over 10, so it's going to be red or pink. Bromothymol blue in a solution of pH 2.8. If we go back here to bromothymol blue, it should still be yellow because bromothymol blue stays yellow at a pH of under 6. Methyl orange in a solution of pH 3. So we'll go to methyl orange. Orange is going to be right. No, methyl orange. And we have a pH of 3. And so this should still be red. Okay, thymol blue in a pH solution of 5. So if I go to thymol blue and a pH of 5, should still be yellow. And litmus in the solution of pH of 8.2. Now this one we don't have to check because litmus paper turns blue in a basic solution. So if we separate samples of an unknown solution that turned methyl orange and bromothymol blue yellow and turned bromesquirrel green blue. So methyl orange and bromo blue turned yellow and bromesquirrel green turned blue. So if we go back to our unknown chart, okay, so we have methyl orange was yellow, and bromesquirrel blue, bromothymol blue, sorry, was also yellow. And then bromesquirrel green was blue. So if we look at our options, okay, bromesquirrel blue, if it was yellow, it has to be less than 6.0. Methyl orange, if it's yellow, it has to be greater than 4.4. And if bromosquirrel green is blue, it has to be greater than 5.4. So if I go back, our pH is likely between 5.4 to 6 would be our pH. So here we'll solve it again. So methyl orange is yellow at greater than 4.4. Bromothymol blue is yellow at less than 6.0. And bromesquirrel green is blue at greater than 5.4. So the pH of the unknown solution is between 5.4 and 6. So this is all about using your data booklet to solve problems. I hope you enjoyed today's lesson on acids and bases. Enjoy.